Hello guys, this is 11.7. We're going to look at conic sections in polar coordinates. Now, before we start on talking about the relationship between Cartesian and polar of conic sections, we want to introduce an idea called eccentricity. Okay, so eccentricity by definition is how much a conic section varies from being circular, right? So how far away are they from a circle, right? So for example, a circle will have an eccentricity of 0 because a circle is a perfect circular. So that uh, the eccentricity shows you how uncircular the curve is, right? Since a circle is a perfect circular shape, right? Then the circle has eccentricity of 0. So bigger eccentricities means that the graph is less curved. Right? First, we have the definition of how to find eccentricity of different shapes, different conic sections. So for ellipse, it's c over a, or we can have the formula right here, square root of a squared minus b squared over a, right? Remember, c is the center to foci distance, center to foci distance. Right? And we do have that formula for both the ellipse and hyperbola. For a parabola, the eccentricity is always going to be 1. Right? And this one does not have any specific meaning, right? It just measures how uncircular a parabola is. Right? And for ellipse and hyperbola, right, it depends on how far away their foci is from center, right? The larger the distance between center and foci, the larger your eccentricity is going to be. All right, so let's take a look at one picture together. All right, so the first one we're looking at is the parabola. All right, as we know, parabola, a point on the parabola has the same distance to the focus, right, which is this red dash line here. That's called that A. And then it also has the same distance to the directrix, right, which will be the same thing as A, right? So in this case, the distance PF is equal to PD, right, which is in our variables will be A equal to A. And in that case, we can actually use the uh, eccentricity formula for the other two. We get E is equal to A over A, which is always 1. And it's 1 for all the points on the parabola, right? That's why we know that parabola has an eccentricity of 1. And next, we have the ellipses, right? So we have two foci, depending on the point. We pick on the ellipse the distance between that point and to the two foci. If you add these two red dash line up, it will be the same for any point on the ellipse, right? And then we can also look at the directrices of the ellipse, right? Even though it's not that common to talk about directrix for ellipse, but in this case, we can use that to calculate um, what our eccentricity for ellipse is going to be. Right. So the formula for the electricity eccentricity of parabola and hyperbola, it's the ratio of the distance between the foci and the distance between the vertices, right? Or c over a, which is 2c over 2a. But we're not going to get into details of these. How we will have a summary on how to figure out all the eccentricities for different shapes. Right? Now, one easy way to differentiate between a parabola, ellipse, or hyperbola by looking at their eccentricity is that a parabola has eccentricity of 1, an ellipse has eccentricity of e less than 1, and hyperbola has eccentricity of e greater than 1. And all these are result of studying these three different conic sections in details, which I'm not going to bore you with. But if you're interested, we do have many detailed information in the textbook. So next, let's look at some examples together. All right. So for our example one, we want to find the Cartesian equation for hyperbola that has a focus 3, 0 and x equal to 1 as the corresponding directrix, right? And we're going to use this figure to help us out with our equation, right? So a focus at 3, 0 means it's going to be on the horizontal focal axis, which is opening to the left and right. And here are a few information that we can know is first, we know that one of the focus is at C0. Okay, so focus at 3, 0, meaning that's equal to C0. That tells us that C is equal to 3, which is the distance, the center to foci distance, right? Center to foci distance. Okay, and what we can do, what we can learn from C is that we can use that later in building our equations. All right, so next thing we want to find out is we know that directrix is x equal to 1. And we also know that directrix, we'll just look at 1 for now, is x equal to a over e, meaning a over e is equal to 1. And what we can learn from here is that a is equal to e. Right? So the value of a is equal to the value of directrix. Right. So let's look at earlier, how do we find the eccentricity of a hyperbola, which is the letter E. Right. So go up, eccentricity of hyperbola is E equal to C over A. All right. So here we know that E is equal to C over A. We know C is 3, right? And A is equal to E, right? So we can write that as 3 over E. Now, by looking at this, trying to solve for E, we have E is over 3 over E. That means E squared is 3. And then we can square root it. E is square root of 3. Now, since E measures how circular a conic section is, it's not going to be negative, right? The smallest we can have is 0, which is a circle, right? So E is square root of 3, which is approximately 1.732. 1.732, right? Which is greater than 1. And that matches with our assumptions earlier. A hyperbola will have eccentricity greater than 1, right? So eccentricity is greater than 1. And next, how do we find the equation for the hyperbola? And here is the formula that we're going to use. PF is equal to E times PD. Now, this formula is not going to make sense now, right? But let's look at the picture, right? So PF is the distance between the point P and the focus, right? And PD is the distance between the point and the directrix, right? So what we have here is that this formula actually tells us by applying the distance formula to find PF and PD, we will get either the equation for a parabola, an ellipse, or hyperbola. Okay, so let's look at PF first, right? So P is any point on the graph, right? P is any point on graph, right? And F is the focus, right? F is focus. In this case, our focus is 3, 0, right? So let's say P is any point on the graph with coordinate x, y, and focus is 3. Then the distance between P and F is the square root of x minus 3 quantity square plus y minus 0 quantity square, right? The distance formula from our regular algebra, right? Finding any distance between 2 points on the line. Okay, so that's PF. And what about PD? PD, right? So PD is the distance between any point and the directrix. Now, since the directrix is a vertical line in this case with equation x equal to 1, so basically all we need to do is just take x minus 1, right? Take x minus 1. Right? And in this case, we want to put them in absolute value, right? Because we're talking about distance between any 2 points. Of course, you can take the square root of x minus 1 square, but that's the same thing as saying x minus 1. Actually, let me write it down. Right. X minus 1 square, which is absolute value of x minus 1. Right? Because we don't care about the y value. We're looking at the shortest distance between any point and the line x equal to 1. Okay. Then we can follow this formula right here. PF is equal to E times PD. Right? So PF is equal to E times PD. And then we have the square root of x minus 3 square plus y minus 0 square is equal to E, which is square root of 3 multiplied by x minus 1. Okay, and let's attempt to simplify this equation, see if we can get a Cartesian equation of the parabola. So first we can square both sides. Right? So square both sides. And we will have x minus 3 squared plus y squared is equal to 3 times x minus 1 squared. All right, let's expand the x minus 3 squared and x minus 1 squared. We have x squared minus 6x plus 9 plus y squared is equal to 3 times x squared minus 2x plus 1. All right, expand the right-hand side. We have 3x squared minus 6x plus 3. All right, so let's simplify this a little bit. All right, minus 6x. And I'm going to move everything to the right-hand side and the constant to the left-hand side. So x and y to the right-hand side and constant to the left-hand side. All right, so subtract 3. Subtract 3 right here. Subtract x squared. And then subtract y squared. All right, what do we have? We have a 6 on the left, and then 2x squared minus y. Like that, all right? And divide both sides by 6, we get 1 is equal to x squared over 3 minus y squared over 6. Or we can rewrite it, x squared over 3 plus, minus y squared over 6 is equal to 1, right? And that is the equation of an hyperbola. Okay, and that's it. All right, we can use the idea of PF equal to E times PD to find the equation for either ellipse, hyperbola, or parabola. And all we need is how to find this distance and figure and identify what the eccentricity is by doing what we did above, right? Given the focus, given the directrix, we can find out what the eccentricity is. All right, so here we have the polar equation for a conic section with eccentricity E. All right, now in this form, we're assuming that we have a vertical directrix, which means we are looking at a parabola or ellipse or hyperbola that's horizontally, right? Opening in a horizontal direction. Right, so in the first two, right here, we have a parabola opening to the left, and notice that here it's a plus e cosine, and then if it's opening to the right, then it's minus e cosine. Right, that's the main difference. And if it's opening up or down, instead of cosine, we have sine. Right, so that's the main difference here. Right, sine and sine. Okay, so that's the four general form for a parabola, right, in terms of polar equations. And this is actually specifically for parabolas. Forgot to mention that. Okay, and next, let's look at the conic sections in polar for ellipse, right? So it's in a very similar form, right? Denominator is the same and numerator is a little different. So we have a times 1 minus e squared over 1 plus e cosine theta. right? And remember, in polar we have r theta, and in this case a and e, they are our constants. Okay, so here's a picture to go with that. Right? So if it's cosine, then we're looking at the focal axis on the x-axis, the horizontal focal axis. And again, we have the constants a and e, right? Where e is your eccentricity and a is the distance between the center and the vertex, right? Which can be found in the equation, in the Cartesian form of that equation. Okay. And this last one we have is the standard polar equation for a straight line. Right? It's always pretty fun to represent just a straight line in terms of polar, because we know that in polar all the graphs are pretty circular, right? We have loops and we have stuff. Right? So here we have one way to represent a straight line in Cartesian, which is just a linear equation y equal to mx plus b in terms of polar coordinates. Right? So let's look at this. If the point P0 is the foot of the perpendicular line from the origin to the line L, and R0 is greater than or equal to 0, then the equation for L is r cosine of theta minus theta 0 is equal to R0. Right? So let's say we have a blue line like that, right? And then you draw a perpendicular line to this, and you get this P0, this point, right? And we can find this point by um, looking by identifying what the coordinate is and the angle based on the line itself. Okay, and then we just need to plug in theta 0 and r0 to complete the equation, which is pretty straightforward. And we'll take a look at an example of that in a second. All right, so next let's look at a few example using the all we just talked about. All right, so let's do an example. Find the equation of hyperbola with eccentricity of 3 over 2 and directrix of x equal to 2. Right, and we can use this general form for parabola and hyperbola. R is equal to ke over 1 plus e cosine theta, where k is positive, it's a vertical directrix. Right, so basically here we can just plug in the information we have. Right, r is equal to k, which is x over equal to 2, multiplied by e, 3 over 2, over 1 plus e times cosine theta. Right, and then we'll have r is equal to 3 over 1 plus 3 over 2 cosine theta. Right, and to make this a little nicer, we're going to multiply 2 over 2. We get 6 over 2 plus 3 cosine theta. Right, and that will be your polar equation for the hyperbola. Right, pretty simple, pretty straightforward. Right? And one thing you want to be careful is that whether it has a directrix vertically or horizontally. Right, if it's horizontal, then we have to change the cosine into sine. Okay, and let's try another one. All right, next we are given the equation of a parabola in polar form, and we want to find what the directrix is, right? So in the general form, the directrix is going to be the value of k, right? So we want to figure out what the value of k is. So let's see. First, that's factor out a 10 from the denominator. We have 1 plus cosine theta. Now, one thing we know about the parabola is that parabola has eccentricity of 1, right? And that is going to be key to solve our equation here, right? So in the form, we have 1 plus e times cosine in the denominator. Now, we know that eccentricity is 1, right? So that means there should be something in the numerator as well. And we can, if we can find out what the constant is, that's going to represent our k. Right? So if we can put 25 over 10, the whole thing in the numerator, 1 plus cosine theta. Right? So 25 over 10, we can write that as 25 over 10 times 1, which will be our eccentricity. Right? That means the other part of the constant in the numerator will be our k. All right, so in this case, our k is 25 over 10 or 5 over 2. And in that case, we can say x equal to 5 over 2 is the directrix. Okay, it's just playing around with numbers and letters. All right, so let's look at one example where we want to write the equation of the line in terms of polar coordinates. And so the line we have is radical 2x plus radical 2y is equal to 6. And here we actually can just replace x and y with r cosine and r sine, right? So we have rad2 r cosine theta plus rad2 r sine theta, which is equal to 6, right? And what we can do now is we can um, factor out the r, right? Like this, radical 2 cosine theta plus radical 2 sine theta is equal to 6. Okay, and uh, what we're going to do here is a little tricky. What I'm going to do is I'm going to divide by 2 like that. Okay, and we have r times rad2 over 2 cosine theta plus rad2 over 2 sine theta, which is equal to 3. And the reason why we're doing this is because we can represent rad2 over 2 as um, cosine pi over 4 and sine pi over 4, like this. Cosine of pi over 4 plus sine pi over 4. And then the rest is the same. Cosine theta, sine theta. Right? And what we have done here is this is actually the formula for cosine of difference angles. Right? And we can rewrite this as r cosine of theta minus pi over 4 is equal to 3. Okay? And this is from earlier when we were talking about different types of trig properties that you can use. But yeah, to write out the equation for polar, you will require some technique like this, right? Divide the number. Usually it's 2, and then you will get some sort of special angle from this ratio here. So rad2 over 2 and rad2 over 2 is what we have in this case, right? So some cases you'll have rad3 over 2 and 1 over 2, which will correspond to some the same angle for cosine and sine. And then you can use the same technique to combine these two terms into just one trig function of the form r cosine of theta minus pi over 3 and equals 3. And that point, right, this point right here, 3 and pi over 4, will be the point at the foot of the line that makes a perpendicular angle to the original line. Okay, and yep, that is it, and that's all for 11.7. Right, and a lot of formulas in here, but definitely you can have this on your side when you're working on the homework. And thank you very much. I'll see you soon.